Now let's go into an element that has electrons in its D shell, such as scandium over here. Now if you're like me, you're probably too lazy to write everything over again from the 1s shell. And that's why chemists came up with this shorthand version called the noble gas configuration. And basically you just start the configuration starting from one of the noble gases, the closest one. And so for scandium, it'd be the closest noble gas would be argon. And we know from the previous example that the electron configuration for argon is 1s2, 2s2, and so on over here. And we can just use this notation, argon, in these brackets, just to represent this whole electron configuration. And then after the argon, we're just going to continue with the rest of electrons that come after it. So it'd be a 4s2 right here. And this is where things get weird after this. You'd think it'd be 3d1, right? In the D block in the fourth. I mean, you'd think it'd be 4d1, but it's actually 3d1. And this is because, if you remember, we had all those 3d orbitals up here for these elements that were never filled. And you may think that the 3d should come before the 4s, and if it doesn't, it'd be violating the alpha principle, but it's actually not, because the 3d orbital has a higher energy state than the 4s2 orbital. I don't know if you remember the energy diagram I showed earlier where you can see this. And this is called degeneration. And so basically the 3d orbital comes after 4s2. And an easy way to remember this, if you forget that the 3d comes before the 4s, is just to remember that the coefficient for this d orbital is the period it's in minus 1. And then you know the coefficient for the d orbital that's corresponding to electrons here. So that's the complete electron configuration for scandium. Now let's try doing palladium, another element with electrons in its d shell. And since the last noble gas we passed before reaching palladium is krypton, we're going to have krypton for our noble gas configuration. And then after krypton, we're going to add the rest of electrons. So we have 2 electrons in the 5s subshell. And then after that, we're going to have the D subshell. And we're going to have a total of 8 electrons in the 4D subshell. And remember, using our method from before, where you do the period, which is 5 minus 1, our coefficient would be 4. So this is 4d8. Remember that. And that's pretty much it for the electron configuration, and I think we're done here. Finally, let's do the electron configuration for elements that have electrons in the f orbital, and one of these is holmium. And to start off our electron configuration, we're going to start off with the noble gas shorthand. And for that, we're going to have xenon, because it's the last noble gas we passed before getting to helium, which is around here. So xenon in first. And then we do the next electrons, which would be 6s2. Now after that, it's going to get different. Instead of being 6f, we're going to have 4f. This is just like the d orbital situation we had before. And this is because, if you remember, every element after argon has an f orbital even if it's not used, meaning that the first f orbital is up here in the 4th period. An easy way to remember this is to subtract 2 from the period number you're on. So for helium, since we're here, it'd be 6 minus 2, and we get 4, as you can see here. And then all we need is a superscript for f, which would be 11, because we have 11 electrons from here to here. And that's the completed electron configuration. The final electron configuration we're going to do is for lutetium. And again, we're going to start off with the noble gas shorthand, which would be xenon, just like the one before, because you can see xenon here, and then we go down to period 6, where lutetium is. And then after that, we're going to have a 6s2 subshell, 6s subshell filled with 2 electrons. And now this is where we have our F subshell, our 4F subshell. And we have, if you count the number of electrons here, we have 14 electrons. Now you think this is where it'd be done, but no, remember, the 14th electron is here, and we still have one more electron to go. And if you sort of put this, the lanthanides and the actinides back into the periodic table, you'd see that it'd end with lutetium up here in this block, and that means it's back in the D block in the first column. So it'd have one electron in the D subshell. So it'd be 5D1. Remember our period rule, 6 minus 1, you get 5. And that's it for lutetium. Now that we've covered the specific rules for every type of subshell, let's ask ourselves, can two different entities have the same electron configuration? And the answer for this is yes. And this is because of ions, because they can gain or lose electrons, meaning that their electron configuration can change, and they can have the same electron configuration as another element. But this also means that they're going to have a different electron configuration than their respective ground state. Okay, so now let's look at an example of the ground state selenium versus its 2- ion, which is the typical charge 2- for selenium. And using what we learned to write electron configurations, we know that selenium in its ground state has an electron configuration of argon 4s2, 3d10, and 4p4. Now for selenium 2-, we're going to start off by writing its ground state electron configuration, which is the same as here. But it's going to be different because we have to add on 2 electrons, signified by this 2- up here. And those 2 electrons are going to go into this 4p subshell, because we can see that our 4p subshell still has 2 electron spaces left, because the maximum number of electrons it can hold is 6, and we only have 4. So our new electron configuration would be AR 4s2, 3d10, and 4p6. Now we're going to look at selenium 6+. And in this one we're going to be removing electrons. So it's going to be different from selenium 2-, which adds electrons. So when removing electrons, you have to remove electrons from the outermost shell, regardless of which order the electron configuration is in. So here we have the electron configuration for its ground state selenium. And if we're losing 6 electrons, we're going to take it first from the 4 energy level, or 4th shell, because that's the highest level. And when we're going to take it from the 4th shell, we have to first determine if we're going to take it from the S subshell or the P subshells. And if you look at this energy level diagram right here, we can see that the P is higher energy level than S. So we're going to be losing electrons from the 4p subshells first. And we only have 4 electrons here. So we're going to lose those 4, and then we still have 2 more electrons left. And those 2 electrons are going to go away from the 4s2. And that's going to leave us with argon 3d10. And you can see that it's very different from the selenium 2-. That's because we lost electrons. Here we added electrons. But you can also, if you look carefully, you can also see that the selenium 2- has the same electron configuration as krypton in its ground state. And you can see we have 1, 2 more electrons. And due to this, you can't just simply have an electron configuration and determine what the element is, or like what the entity is, unless it tells you that it has to be an element. Alright, so finally I want to go over some important exceptions when you're doing electron configurations. And there are 2 main exceptions you have to keep in mind. And these are the electron configurations for copper and chromium. Now the expected electron configuration for copper and chromium are these right here. But they have a different electron configuration due to problems with stability. And that makes their actual ones these right here in red. As you can see for copper, copper has one half-filled 4s subshell and one full 3d subshell, whereas the expected one has one full 4s and one just incomplete 3d. And for chromium, you have 4s subshells and a 3d. You have a 4s subshell and a 3d subshell that are both half-filled, and that's different from its expected, where as a full 4s and just an incomplete 3d. So what you can notice here is that half-filled subshells and full-filled subshells are more stable than incomplete ones. And also, the complete full subshell is more stable than a half-filled one. So keep that in mind when you're doing electron configurations, because that might turn out to be an exception with one of your elements. And finally, I hope this video helped you, and we wish you the very best of luck in your chemistry class. So make sure to like the video and subscribe to Flight Notes for more videos on chemistry, economics, and many other topics.